Okay. So we were discussing about the quantization topic, and we did a few things, a couple of things. We first found out that under the assumption of uniform quantization or uniform distribution of the input data within a range from -a/2 to a/2, a range, a data magnitude range spanning a range of a, then with R bits, using R bits, which makes 2 to the R level quantization, we come up with a situation that the distortion is related to d square over 12. Okay, that was from the integration. Although we didn't do an extension to this, could be to think of what would be the distortion if the distribution is not uniform, but it may be, I don't know, perhaps triangular. For instance, within the range from -a/2 to a/2, a uniform distribution, probability density function would make a probability density function to be precisely equal to 1/a for all the points on the range. It will be the same 1/a, but if it is triangular, for example, it would be more towards the origin, towards the center of the distribution, and it will decay to the tails. So, for instance, what could be the distortion in that case if you try to integrate, if you try to simplify the integral? It would be, of course, a little bit more difficult than a uniform distribution, clearly, but it maybe such a thing may be a question. By the way, notice that the probability density function distribution must integrate to 1. So that's why the range was a. Therefore, the height is 1/a. When you multiply them, you get the area, the integral under the probability density function, which is 1. But if it is triangular, you have to find the peak value accordingly, right? That's a different, that may be a different entity. So construction of this integral for those different ways of visualizing the probability density functions is a possibility of questions that you may come up with in the final, for example. So this may be an example PDF, triangular PDF. Another example is even more difficult to attack, and that is, for example, half is something, the other half is something else. Okay, they all integrate to the same one, but how would you optimize these quantizers, first of all? And with these optimizations or with uniform quantizations, we didn't talk about optimization yet, so let's assume you have uniform quantizers. With uniform quantizers, what would be the distortions under these two cases that I have drawn in blue? Of course, the uniform quantizer is the optimal quantizer for the uniform distribution, we can say, because you notice that we can see that within this kind of an interval, if inside your probability density function range, if you put the quantization output to the center of the quantizing interval, then that would supply you with the minimum distortion, because the distortion is the amount of error that you integrate to the left and to the right. For instance, if you don't choose this central value, but if you choose somewhere else as the output of the quantizer, then the distortion towards the left will be too much. And in the square integral sense, the integral that you will get with the red crossed point to the left and to the right will provide you with a larger distortion. So that distortion is minimized in the center. But if it is not uniform, then we may come up with situations like from here to here, for instance, okay, inside this distribution, which is not flat, as you see. And since it's not flat, where would you suggest to put the central point, which is the quantizer output value that we are trying to optimize? We will see that we have two optimization criteria, one for the encoder, one for the decoder. Now I'm trying to optimize the decoder, which detects where the output should be. If you put it in the center like this, then you will notice that in most of the cases, the output will be to the right of that point. Therefore, we know that in a majority of the cases, we would be here, and in a minority of the cases, we would be here. So is that point really the point which minimizes the local distortion within that region? So we have a region and we are trying to represent that region with a value at the output. What is that value is the thing that we are trying to optimize. Let's roll back a little bit. What I'm talking about is this point, which, as you see, located at delta over 2 plus the starting point, which is delta over 2 minus the ending point. That's the average. That's the mid value for the uniform quantizer case. So I'm trying to find out what this should be so that this integral within this range would be minimized. So when we focus to here, we can see that probably a point somewhere here would be a better point this time, because to the right of it will be more balanced with to the left of it. So if we split it like this, this red point is most probably such a point that the area of the left is equal to the area of the right. So that to the right and to the left of it, there's an equal probability of encountering, which makes at least the probability, the mean value of the quantization error to be 0. Otherwise, there would be a bias. So the quantization error mean value is expected to be 0. But this is just intuitively. I didn't prove anything. I didn't express the distortion integral, the error integral, which is the square of the error, and I didn't minimize it. This is just something that I'm telling intuitively. Now, we will continue with an algorithm which provides us with a method, not the intuitive thing, but a true methodology for the optimization of a quantizer. And this decoder quantizer that I'm talking about is only a part of it. It will be more than this. So let's give a title to that. That is the optimum quantizer design. The optimum quantizer design consists of two things: the decoder optimality as well as the encoder optimality. Encoder and decoder optimalities. The encoder optimality has a meaning. It is telling us that if you have a decoder, so you fix one of them for the optimization of the other one. That's the algorithm that we are going to run. It's not an analytical way of solving the question, but it's an algorithmic way of attacking the problem. the optimal encoder depends on the decoder. So the decoder is telling me something. Let's start with, therefore, the encoder optimality. So we have fixed or determined the decoder, let's say, in a previous step. And the decoder is doing what they are telling me, what the output values are. Let's say that the output values are here, 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 and here. Just some random, it shouldn't be random, of course, it must be optimized as well. But initially, suppose that we are in this kind of a situation. So with this decoder, the decoder is therefore notated by these crosses, which tells me the output points, and the encoder will be notated with these dashes or lines. In fact, I would be using vertical lines because those lines will indicate the boundary, the region of the corresponding decoder output. Previously here, I said that these are the boundaries. So we define a region, and inside that region, I'm going to represent it. And that representation is this red dot that I have drawn. Now, the other thing is, if this red dot is given, what are these boundaries, these blue boundaries? And the encoder optimality tells me that it is such a boundary that gives me the minimum distortion. So I'm thinking of these as the boundaries that separate between the decoder outputs. And that thing is notated or expressed with this terminology known as nearest neighbor. This nearest neighbor optimality is this kind of a thing. So if you come up with a sample on this axis, so we are doing scalar quantization basically. On this axis, let me draw some green points. Suppose that your green point is here. It's a data point. This data point should be quantized into a region which is represented by one of these red crosses. So which one should I choose? I choose the one that is nearest to. I choose the output which this green point is nearest to. And what is it nearest to? It is nearest to this red cross to the left of it. All the other red crosses are farther away from this green point. This one is, for instance, farther away. This one is farther away. This one is farther away. So I'm trying to minimize this distance, the selection of these green points according to the distance. So let us focus to this red cross here. Within which range of green dots will they be represented with this particular red dot that I'm indicating, this red dot? As long as all the green points, input points, are between this line and this line, they are nearest to this output. So if this green is falling in between this range, anywhere within this range, they will all be nearest to this particular output that we have. And I'm going to represent it with yj, Okay, it's just the value, it's the jth value. The one to the left of it will be yj minus 1, and the one to the right of it will be yj plus 1. Okay, just these decoder outputs are over there. So we have yj plus 1 here. And let me try to make this a little bit thinner. And this one is yj minus 1. So the nearest neighbor rule is dictating me that I have to choose a region which is determined by this nearest neighbor. Let me go back to the original thickness. So what are the crossing points of these vertical lines then? What is this point, for instance? What is this point, and what is this point according to the nearest neighbor rule that we will be using? This point I am going to say xj, and the other point I'm going to say xj plus 1, because they are also in that kind of an order. And this point, for instance, will be xj plus 2. And this point, by the way, is xj minus 1. Okay. So what is xj? What is xj plus 1? What is xj minus 1? If we know yj minus 2, yj minus 1, yj plus 1, and yj plus 2. This is why, oops, it's blue. Let's make it with red. Yj plus 2, and this point is yj minus 2. Okay, so what's the relation between yj's and xj's? And the relation is this: xj is equal to, which is the boundary between yj minus 1 and yj, is equal to just the mid value, yj minus 1 plus yj over 2. Just the central value. Okay, and similarly, for instance, xj plus 1 is equal to the middle value between yj and yj plus 1. So this is where this line is crossing the horizontal data axis. This point. This point is xj, and this point is xj plus 1. So the nearest neighbor works this way. But of course, it all depends on the minimization. So these are as a result of minimization of the distance between the input point. Let's call the input point x, the green point, that is, and yi, in terms of which I would be the smallest. So this will be your j that you choose. That defines your region. And from this minimization between minimization of the distance between the input and the outputs, the minimum distance will give you the so-called nearest neighbor classifier. You can call it a classification because it's like classifying anything between this value and this value to this class, and I'm representing this class with an output corresponding to yj. Okay, that's the class representer, and between these 2 points, it's a class. Between these 2 points, it's another class. And its representation is here. Between these 2 points, it's a different class, and the representation of this class is here. The boundary classes to the left or to the right, they start at this boundary, and the other boundary is plus infinity. It's there. and everything between, every input between this value and infinity will be nearest to this output, and they will be represented with this output. Similarly, the left boundary, the leftmost boundary is minus infinity. So I can literally say that for this case, yj minus 3 is equal to minus infinity, and yj plus 3 is equal to plus infinity. For the selection of j, of course. Otherwise, you must give numerical values. And how many regions do I have? It depends on how many bits I'm using for quantization. If I use r bits, 2 to the r regions must be appearing along this input axis. This vertical axis, by the way, is not a vertical axis. It's just showing the 0 points. We don't have a vertical axis here. It's just the 0 points. So it's just a horizontal line that we're talking about. We don't have a vertical axis value. All right. So this was related to the so-called encoder optimality, and it is done by the so-called nearest neighbor, and the nearest neighbor induces this, which is the midway between two output values. This midway is unfortunately valid for one kind of a distance. So if you choose this distance to be one thing, which is the Euclidean distance, the distance that we use, the square distance. If you're using, for example, absolute difference between two things, then the distance will be different. Or if you use infinity distance, it will be different. I will talk about the distances or the distortion matrix that we may use in a little while, but not now. Let's continue as the normal Euclidean distance matrix, which is this. Now the next thing is decoder optimality. Now this time on the axis, data axis of scalars, we don't have the representation values which correspond to the decoder, but because we are going to optimize the decoder, but instead we have the encoder. And the encoder, as you may remember, determines the boundaries. I want to do it similar to the previous shape a little bit, as much as possible. So it was like this. This was the 0 point. Okay. So we found from the previous iteration, let's call, we found the boundaries like this, because that's what we have optimized. So let me make it a little bit thinner, like this, and say that this is let me focus to the xj minus 1. This point is xj. This point here is xj plus 1. And this point here is xj plus 2. I guess it was like that already. Yes. So we have these boundaries. The decoder optimality now takes a look at the following. If you are within a range, if you are, let's say, between xj and xj plus 1, if you are here, how would you represent it? What would be the best representation? The best representation within here depends on the distribution within this interval. If it is flat, for example, you will clearly say that yj, which falls within this range, should be the mid value, like xj plus 1 over 2, the mid value. But if its distribution is tilted, or it may have an arbitrary distribution between xj and xj plus 1, how would you choose it? And the optimality here suggests that the decoder point must be the centroid. These are too thin. So we have to choose the output here to be the centroid, which is the center of mass of that distribution, on the condition that it is within this range. So it may be, I don't know, somewhere here, for instance. What could be the distribution for that to be like this? Maybe something like this, a little bit tilted up towards the right-hand side. And the centroid rule tells me that when you split from this point of yj to the right and to the left of its areas should be the same. Okay, that is the centroid. And similarly, between this region and this region, the centroid should also again be adjusted. It may be, I don't know, here. So this may be yj plus 1. And within this range, maybe it's somewhere here. So this is yj minus 1. And then I have something like this to be yj minus 2. These new red crosses are the centroids of the corresponding regions, according to the probability density function. Just I found them to be like that. Those are the center points. And when you find the center point, we call it the centroid. That's why I'm saying that the decoder output values are the centroids of the corresponding regions. And the region boundaries between two centroid values is the encoder optimality, and that is the nearest neighbor rule that we have. So now you can notice that from the top figure to the bottom figure, I started with these yj's, these points, and then I found these boundaries to be the optimal, and then I used those boundaries to be optimal and found these centroids to be optimal this time. And you may see that these centroids are essentially different from the centroids in the previous step. See that, for example, this was to the left side of this range from here to here at the top figure, but now it is to the right, so it moved. And this one from the right to the left, it moved. This one also moved a little bit towards the left. And this one moved to the right, and this one moved a little bit to the right. So they move, which induces a new set of decoder outputs. So what am I gonna do? I'm going to readjust. I have to readjust these boundaries once again, because they're not now in the centers between yj minus 2 and yj minus 1, for example. This line is not crossing from the mid value of these two. It is to the right a little bit. So I have to adjust it a little bit further to the left. And these two outputs, between these two outputs of yj minus 1 and yj, this is not in the center anymore. I have to move it to the right a little bit. And this line between these two outputs must be moved to the right a little bit, and it must cross somewhere here. This probably will not change because it seems to be almost in between yj plus 1 and yj plus 2. So I am moving this time these boundaries. I'm moving them. So is that the end? No, this time the boundaries have moved, so I have to readjust these outputs once again because the boundaries changed. I have to find their centroids. So the centroids move again. When the centroids move, the boundaries must be readjusted. They move again. When the boundaries move again, the centroid outputs must be adjusted as well. So it's an iterative step. Let me indicate it with a red. So what I'm doing is I'm making this kind of an adjustment and do the other adjustment. And when I do the other adjustment, I come back and do this adjustment again and again. Technically, indefinitely, of course. But after some time, these adjustments tend to slow down. They don't move a lot. In fact, they don't move at all. You may put a threshold to the movement measurement if the movements, overall movements, total motions in either yj's or xj's, if those motions are small enough, then you may stop. That is known as, there's a name to this kind of iteration. It is known as this thing is known as the Lloyd max iteration. So we do the so-called Lloyd max iteration. Once that Lloyd max iteration stops, we call it a Lloyd or a max quantizer. Okay. And these conditions of encoder optimality and decoder optimality, this one and this one, they are also known as Lloyd conditions. So I will now put some analytical expressions to these Lloyd conditions. From one, which is the encoder optimality, the distortion, which is the expected value of distance between x and qx, needs to be minimized. So this minimized expected value is, sorry, I have to put it like this. Let me erase this part. Is always greater than or equal to a case which gives you the minimum, which is given like this, the minimum among i's, the distance between x and yi. Okay, there is such a minimum choice of that kind of a yi, and therefore that choice determines the boundaries. So the region we are going to indicate it as Si is given as the value of all possible inputs. So it defines the range. Si is the range itself. For all inputs or all inputs in a range such that this I is equal to the arg minimum of let's say this time k, because if I use I again, that I is arg min I would be a little bit mathematically incorrect. Which is nearest to yk. So this range of x the range of x values, which is nearest to yk, determines this ith region. This is called the nearest neighbor encoder. This one is known as the nearest neighbor encoder. And the nearest neighbor encoder, interestingly, automatically gives us boundaries to be between the middle value between two neighboring outputs, yk and yk plus 1, and we draw a line just in the center of it, which is yk plus 1 over 2. Passing from there, we draw the boundary. The other boundary is between yk minus 1 and yk. The other boundary is between yk plus 1 and yk plus 2, etc. So that is the nearest neighbor rule, which is the first condition of among the conditions known as Lloyd's conditions. And the second one, in an analytical way of putting the expression, is the mean squared error quantizer. I can say it like that. I'm still using square because it's a common name, but if you don't use square distances for distortions, then the name also changes automatically. But this is, if you use square, then this is mean squared error quantizer, which gives you the decoder optimality. The decoder for the mean squared error quantizer is the summation for all boundaries, for all regions of SIs that we found here. So for all i's, and within the corresponding region of SI, we integrate all the inputs with a yi. We find these distances, and this is the expected value of the distortion that we have. This dx comma yi is the distortion. You could write it like x minus yi in parentheses square. Then that would actually be a mean squared error quantizer. Let's write it then that way. Within this region determined by the nearest neighbor encoder, x minus yi squared times the probability density function. So this is the overall distortion. Let's call it D. This distortion needs to be minimized. We have to minimize this, but this is equivalent to minimization of only one of them, because if we can individually minimize these integrals, then their sums will automatically be minimized. So we have to find the optimum output for each region individually. If we found the optimal outputs within these SI regions one by one, their sums will also be minimized. So this is equivalent to minimizing one term of it. Sorry, there is also the probability density function. This one. And the minimization of this now tells us that yi is supposed to be the expected value for the minimization of this integral, the expected value of x, given that x is inside this range. So this output, the centroid I have previously called, this centroid is the expected value of the data within this range. What is the expected value? It's the definition, right? This one is essentially the definition of the expected value, which minimizes this kind of a distortion. So expectation is the mean, as we all know, and yeah, it minimizes this distortion, square distortion. So the mean of this region is the thing that we are trying to find, which is the decoder optimality, also known as the mean square quantizer. So we have 1 and 2, and the Lloyd max iteration runs as 1, 2, 1, 2, 1, 2, etc. There are some technical issues regarding this Lloyd max iteration. For example, which one do you start from? It could be 2, 1, 2, 1, 2, or it could be 1, 2, 1, 2, 1. Well, it doesn't really matter. And where to start is unfortunately an important thing. In other words, if you have some initial conditions, if you have an initial output operation, then from the data, if you are trying to optimize, that's what we do, by the way. We don't really work with probability density functions. We work with data. I may give you 100 values within the range between 0 and 1, for example. Within this range, I can give you 100 numbers, and I want you to find the optimal quantizer, let's say 8-level quantizer, 3-bit, 8-level quantizer. So what are the quantization intervals and what are the quantization outputs? By the way, if you know one of them, the other one is automatically determined. So from those numbers, maybe if you know the range, if you know that the range of input is between 0 and 1, you may say that I split it as 0.1 increments. So I start by the uniform quantizer. From the uniform quantizer, I run this Lloyd max iteration, and they will adjust a little bit, fine tune a little bit, and it will stop. Or the differential improvement will be very small. Then I stop at that point. Yeah, that's a good way of starting the Lloyd max iteration. Otherwise, if you say that the outputs are not 0.1, 0.2, 0.3, but if they are 0.5, 1.5, 2.5, and some 10 values from there, you will notice that only the one related to 0.5 will have all the population within its range, SI. So within one SI, there will be all the data, and all the others will have nothing. They will empty out. So this Lloyd max iteration, although it gives the optimum quantizer, it gives you the suboptimum quantizers, depending on the initial condition where you start this iteration. For instance, in this problem, I started with some initial yj's here. I said yj minus 2 is here, yj minus 1 is here, etc. And then I found these boundaries accordingly. But if I start with another initial condition of yj's, it will give me different boundaries, and it may or may not converge to the same output if you start with these initial conditions. So this Lloyd max iteration is initial condition sensitive, and there are methods to overcome this sensitivity and truly come up with the so-called global optimum instead of a local optimum quantizer. There are ways to do that, but we will see those methods after we see an improvement of this, which is known as the vector quantizers. These are scalar values. The values are quantized, so we have a range of values, but a vector quantization is a different animal, and we will have to see those things as well. Now, before giving a break, in the last 10 minutes of this hour's lecture, I want to indicate, I want to give you an example first. Or, yeah, we will see examples later. So I will continue with some of the properties of this optimal quantizer. I will list them down here. These properties of the optimal quantizer are automatically achieved, but when we list them down, they also help us to understand, have an understanding about the phenomenon of an optimal quantizer. They obey some properties. And these properties, by the way, they are not just facts or de facto. They can be proven. In fact, after the break, I will prove a few of them. And I may ask the proofs of the others, the rest of the things that we will not discuss as take-home exam questions again. The first one is the centroid. It is telling me that from the decoder optimality that I said here, the mean of SI must be, the expression essentially corresponds to this. Within this interval of SI, x fx dx divided by within the same region SI, fx, probability density function dx, which is essentially meaning the expected value of x, condition that it is inside SI. So this is the conditional mean, also known as the centroid. So this is how we find yi. The mean of x is inside this region. By the way, this is all very analytical, and there is no way that we truly apply it for the data. For the data, the centroid really corresponds to the mean or the average, because average is the approximation of the mean from data. How do we do that? We just observe everything within this range of SI. We add them up and we divide by how many observations we have. We found the average of it. That would be the mean, the conditional mean. What is the condition? The condition is that it is inside this region or range. So yi is the centroid. It's property number one. The property number two, the quantization error, which we will denote by epsilon. This is the quantization error. Okay. Condition that the input was inside SI is equal to 0. And that's why we have to choose the centroid, because to the left of it and to the right of it, when you sum them up, the quantization errors sometimes will be positive, sometimes will be negative, and they will cancel out, and the expected value of that error is equal to 0. It's not a square error that I'm talking about. It's just the error in its pure form. So it may be a negative error. Sometimes the input is less than the representation. So the input minus the representation will be negative. Sometimes the input will be greater than the representations. Therefore, the input minus the representation will be positive. And the positives and negatives must cancel each one out. And its average must be equal to 0. And this is valid for all regions of I, by the way. And from that, it's simple to show that then regardless which region we choose, the expected value of the error is equal to 0. It's the expected value 0 in this range, in this range, in this range, they are all zeros. So overall, its expected value is 0. the fourth property is, this is an interesting one, and it requires some knowledge of random processes. And I think the first and this one are the most critical ones. So I will do that in the next hour after the break, so that you will be able to do the others. Maybe I will also do the second one as well, but the rest, it will be easy for you to give the answers. This one, sorry. The fourth one is the following. It's telling me that the expected value of the output, which you can also call it to be the quantized version of this, the corresponding input, times the quantization error is equal to 0. By the way, we had the same, in fact, exactly the same observation for prediction or predictive coding as well, for which you were responsible in the first midterm. In the predictive coding case, it is saying that the prediction times the prediction error expected value is equal to 0. This time it is the quantization times the quantization error expected value is 0. And if you optimize things, this property comes out. It is also, it can also be sometimes represented like this. The quantization is orthogonal to the quantization error. Why is it like this? Or when you think of orthogonality, then we are talking about linear algebra and we're talking about geometry. So if something is orthogonal to the other one, you can imagine it like this. If the quantizer output is not orthogonal to the error, then it means that the error is not minimum. It still contains some information from the input and from the quantizer. But we want to minimize it. Okay, that's the whole idea for the optimum quantizer design. Since we are trying to minimize it, it must contain no information. It must have no relation to the input or the quantizer output. Otherwise, that would still mean that we have things to optimize. We have to optimize the quantizer a little bit so that the error has nothing related with the input or the quantization output. Only then it would be a zero mean random noise, which can be considered as minimized. That's the minimization of the quantizer error. And we will see that. The fifth one is the expected value of the squared error is equal to, this is an interesting one, and you will have to work on it. I'm talking about, or we are assuming that the input is zero mean. Okay, let's do it that way. This squared error is equal to the variance of the input minus the variance of its quantization output, which is, this can also be written as sigma yi square. Okay, so as you see, if the representations are representing the signal in a high fidelity within a good reconstruction, then the variance of this yi will automatically be close to sigma x squared, and this difference between these two will become smaller and smaller. So the best quantizer is, of course, no quantizer, which means the quantization output is exactly the same as the signal itself. Then it will be sigma x squared minus sigma x squared. Excuse me. All right. So this is the fifth property, but this is more than a property. It's just some observation that is quite natural to make. But its proof is a little bit more involved than that, so you will have to work on it a little bit. The sixth is expected value x times epsilon is equal to the negative of this. This x, by the way, is the thing that, or the set that we are quantizing. And as you see, it's not orthogonal to the, it's like the current sample value in predictive coding. The current sample value to be predicted is not orthogonal to the prediction error. It has a relation. So we have this kind of an observation, this kind of an output as some residual error relation. Now these are properties of the optimal quantizer. They are not valid for any quantizer. If you just do some uniform quantizer, where the uniform quantizer may not be optimal, then of course these conditions, these six properties will never hold. They won't be valid in that case. These are valid for optimum load quantizer, when both the encoder optimality and the decoder optimality are satisfied. Now at this point, I think we may give a break. After the break, I will continue with the proof of this first property that we come up with. And you will notice that these proofs are, in fact, like gimmicks. It's not really, I'm not really doing some fancy things. I'm just writing down the definitions and writing alternatives of those definitions and redefine things, and we come up with this kind of an expression. So don't exaggerate the difficulty of the proofs of these properties in your head, because they are actually easy, but they are just awkward. And if you're not familiar with that kind of making proofs, then you may find it a little bit difficult, but actually you will see that they are not very difficult, as you may guess. Okay, so at this point, we can give a break. We will meet at 11 o'clock. Sorry. At the same place. And if you have any questions, or if you can come up with any questions, you may start asking them in the beginning of the next hour. If you may have a question regarding the exam, you may still ask for them in the beginning of the second hour. But before that, let's now give a break. So see you at 11 o'clock.